Okay, so welcome back to the course series, and of course we are slowly delving into more and more of the depth of the course. I'm so excited for it. So today we'll be covering in another interesting topic, and it's called as adversarial search. So I'm still continuing on my search, and therefore all the assumptions already they laid down are intact. They are right in place, except for today I'll be talking about not one agent but multiple agents. To start off with just 2 agents, and my search will be competitive. So both the agents, they'll fight for one common goal, and only one of them can do it. So if the first agent gets it, the second is at a loss. If the second agent gets it, the first is at a loss. So the agents will fight and do everything into their capacity in order to really win the particular thing up, and that's how my search is gonna behave. And therefore the more interesting name of this is game playing. So we'll literally be playing games in this class. How exciting. Now I'll start off with a purely competitive game. So as I said that in multiple agents, many times the agents may cooperate, many times they may compete, and real life may be a mixture of both of these. Why we love games? Because unlike diplomacy of real life, games are as straight as possible. If I win, you lose. If you win, I lose. And therefore, let's say that we'll consider games of a particular kind which are called as a zero-sum game. Now, zero-sum game virtually means that if my score is +1, that's me, your score is -1, I win, you lose. If my score is +10, your score is -10, I win really nicely. I beat you like anything. If my score is -3, your score is +3, I lose, you won. And if my score is 0, your score is 0, it's a tie, at least for this match. So these are the kind of games that we will be modeling. As you can see, it's purely competitive because the higher is my value, the lower is your value, and the sum of my score plus the sum of your score is a big fat 0. So under this strict assumption, let me give names to me and you. Let's give names to a computer player and the human player. Let's give names to the player against which the human is playing, or the player which I will be programming for, and hopefully that will beat you in the game. So I call myself, which is the computerized player, which is the player that I am programming as Max. And therefore the other player, which is you, who is playing against the computerized player, is what is called as a min. Now, there's a reason by which we do that, and the names are particularly interesting. The names are derived from the fact that if at a particular state S, I have US, or the utility of state S, this is basically the expected payoff for Max. That means if we are in a game and the game is going on and we are at a particular state S, what is the score that I expect? What is that final plus 10 plus 5 plus 3 that I expect? That is what is called as a utility of a state, which is the payoff, which is the final score, which is the final how much I win for max. Now, at a particular state, if my expectation is that I get US, which I want to maximize, I want to get as much as high score as possible, I want to get a +1, I want to get a -10, what do you get? You get a -US. So this is the expected payoff for min. Because of course what I get plus what you get, they need to sum up to a perfect zero. It's a zero-sum game. And therefore what do? I try to maximize my expectation. I try to take actions. I try to make those moves. I try to play as good as possible so that my utility or US is maximized. On the other hand, what do? You make sure that US is minimized. In doing that, you maximize your own returns. So you are maximizing US, you are maximizing -US, I am maximizing US, you are maximizing your chance of winning, I am maximizing my chance of winning. We are taking actions in this format. Fortunately, unfortunately, your objective is exactly contradictory to my objective, and therefore when I say you try to maximize your objective, you try to minimize my objective, and that's why I call as myself as the max, the one who maximizes US by selecting improper actions, and min, the one who minimizes US. So let's look at how will we really be doing across this maximization and this minimization thing. However, to start off with is another interesting definition, and that has got to do with what is called as a strategy or a policy. You hear these so many times in games that, okay, what is your strategy in this particular game? Now, remember last week, what we did was called as search, and it's search again. However, last time, all that I said was that, classic example, this is some kind of a grid. I start over from here. All this is obstacle. I need to go here or the goal. And therefore, I would say that my path is 1, 2, 3, 4, 5, 6, or this set of states. So let's call them as 1, 3, x-axis, y-axis. Then I have 2, 3. Then I have 3, 3. Then I have 4, 3. Then I have 4, 2. And finally I've got a 4, 1. And the actions, of course, I'll write it down above over this. It says right, 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 down, down. That's what's called as a path. And I said last time that you can blindly follow that up. The environment is not gonna change. If you take an action, you will succeed in taking that action. It's deterministic. So you could virtually close your eyes and execute this part. No, nothing is gonna happen. Now, unfortunately, I cannot do that. In games, I could say, what do I do currently? However, my next move depends upon what the opponent does. As an example, the game we'll be looking at is the tic-tac-toe. If I play cross, now I don't know what is my next move. If the opponent plays this, I probably will play this. If the opponent, on the other hand, plays this, I probably will play this. So what am I supposed to do is dependent on my opponent, and I do not know what my opponent does. Because I do not know what my opponent does, I can no longer plan a path. It's not that simple now, and therefore I will plan a policy or I will make a strategy. Let's define that up. I denote as pi, and I say policy of a state S is equal to the action to be taken so as to maximize the expected returns, or so as to maximize U of S. Now, what's interesting about this, of course, there's something which is interesting about this. Path was just a linear sequence. So it's just a linear sequence. However, on the other hand, policy is defined for every state possible, which means all that I'm saying is, if the game state is this, this is what I do. If the game state is that, that is what I do. If the game state is this, this is all I do. It's all pre-decided. And that's exactly how you have heard the term strategy in games, a FIFA match. Okay, if Ronaldo is over there, that's what you'll do. But if Messi is around over here, that is what you'll do, and so on and so forth. So for everything that the opponent could do, for every state of a FIFA match possible, you have a strategy. What will I do? You don't go into a game and say, hey, that is an interesting move. Let me think what to do. So that's what you try to plan. That's what you try to compute. That is, for whatever the opponent does, what is my action gonna be? And that is how path differs from the term policy. And know that very well, because we'll also look at the same two terms right at the end of the course. There, I'll just say that it has already been explained. Now, because I'll start drawing, that's the fun of AI. You draw more than anything else. And therefore, let me give in some symbols. So let me say max is upper triangle, min is this lower triangle, so that I don't have to draw it up again and again.